All right, this is Physics Unit 4. We're talking about projectile and circular motions. We've looked at straight line motion. We've seen two types. Uniform motion, where some examples are the air track or frictionless surfaces, and accelerated motion, things like free fall or dragsters that start from rest and speed up. These motions were either in the x direction entirely or the y direction entirely, except for a few ramp problems. So these motions were one-dimensional. Unit 4 will discuss more complicated motions, motions that are in both the x and the y directions at the same time. Two-dimensional motions. The types of motion, their definitions, and some examples. So the first is projectile motion. This is motion that is in the x and y directions at the same time. So an object is going out and down at the same time, or out and up at the same time. The motion would look something like this. So here's the object, it's going out and up. Or something else going out and down. Some specific examples, things like kicking a football, throwing a baseball, or shooting a basketball. These are all objects that would be moving out and up or down. Then there are some military actions, things like dropping a bomb or firing a gun. Then we have uniform circular motion. This is things that are in motion at a constant speed going around a circle. Things like riding a merry-go-round, or if you tied a rubber stopper on a string. When you move it around, the rubber stopper will travel in a circle. There's also examples of a car rounding a curve. Now, this one is not an entire circle, but for some period of time, it is moving at a constant speed, and it is in a circular motion. First, we'll talk about projectile motion. So if you have the notes, you'll see a piece of graph paper, and we'll have to come back and talk about that in a different video. Projectile motion has both vertical and horizontal motions at the same time. The good news is that these two motions are independent of each other. It makes it easier to work with because we only look at the horizontals and then we only look at the verticals. We'll calculate vertical things separately from horizontal things. So horizontally, a projectile's motion is uniform motion. Uniform motion tells us a couple of things. Number one, no net force. No net force means no acceleration, which means that the horizontal velocity, Vx, is constant. Uniform motion, just like the air track. Your other formula, horizontal distance, dx. The horizontal distance equals the horizontal velocity times the time. These are the two formulas that we'll need for the horizontal component of projectile motion. From the vertical standpoint, a projectile's motion is always accelerating. And we're looking at this just like dropped objects. So accelerating. First off, we're talking about a net force. Some sort of net force is present. In this type of a problem, the net force is caused by gravity. The formulas that we need the vertical velocity equals acceleration due to gravity times time. And this comes from a related formula from a previous unit. Final velocity equals initial velocity plus AT. So this is the main formula as we knew it. This is the formula that we'll need. Finally, and this is the last one, so we've talked about velocity, we've talked about distance. Horizontally, we've talked about velocity. Now we need distance vertically. The vertical distance equals 1/2 times the acceleration of gravity times the square of the time. And this comes from a previous formula also. Distance equals 1/2 AT squared. So these are the four formulas that we use for projectile motion. So you want to come back and look at these. We're going to use these a lot. So on this strobe photo, draw velocity vectors on both objects. Assuming that the projectile was launched horizontally at 20 meters per second, and we're also going to say neglecting air resistance. Air resistance makes things extremely complicated, so whenever possible, we want to ignore it. So we're talking about being launched horizontally at 20 meters per second. So let's first look at just a dropped object, and then we'll come back to this projectile. A dropped object at time 0 seconds is going to have a velocity in meters per second of 0. A dropped object at the moment it's dropped starts with a velocity of 0. After 1 second, the velocity will be 10 down. And here's my vector, 10 meters per second down. After 2 seconds, I'm continuing to accelerate. The object is now moving at 20 meters per second down. We'll make this velocity vector proportionally longer. At a time of 3 seconds, our velocity is now 30 meters per second down. So now we're going to compare this dropped object with a projectile. This projectile is launched directly horizontal at 20 meters per second. And so at time 0, here's what's happening. It's being launched directly horizontal. After 1 second, and this is important, so let's think about the velocity x from the previous page. The horizontal velocity in projectile motion is constant. And so at this next instance, the horizontal velocity is still 20. But it's been flying through the air for 1 second, which means it has a vertical velocity. And that vertical velocity is 10 meters per second down. At time of 2 seconds, Vx is constant, which means it's still moving sideways at 20. It's been falling for 2 seconds, and its vertical velocity is now 20 down. At a time of 3 seconds, Vx is still 20, but now the vertical velocity is 30 down. So the horizontal velocity of the projectile at time equals 3 seconds. It's 20 meters per second. The vertical velocity at time equals 3 is 30 meters per second down. So now we're going to find its actual velocity. So here's how we do it. Rather than using the formulas, we're going to start with a picture. So its vertical velocity is 30 down, its horizontal velocity is 20, and this is its actual velocity. This is its actual velocity. So when we want to know its actual velocity, we're going to use the Pythagorean theorem, because what we have here is a right triangle, because we're talking about exactly horizontal and vertical. We have a right triangle, and we're looking for the hypotenuse. So a squared plus b squared equals c squared, or we would say the velocity equals, this is the shortcut method, the square root of 30 squared plus 20 squared. And so we find that the velocity is 36.06 meters per second. Then we're going to need to find the angle. And this is not for every question, but this one is asking for velocity specifically, which means we have to know the direction. And the way it works with projectile questions is we are going to find its velocity from the vertical. So this angle is the angle from the vertical, and this angle is the angle from the vertical. So when we want to find theta, theta is the inverse tangent of 20 over 30. And it is 33.69 degrees from the vertical. The projectile hits the ground 5 seconds after. Find the speed of the impact. So if we want to know velocity in the y direction, we know that it is acceleration of gravity times the time. Acceleration of gravity is 10, the time is 5, so we're looking at 50 meters per second. So 50 meters per second down, 20 meters per second horizontally. Here's our parallelogram method. And this is the actual velocity. So velocity equals, we're using the Pythagorean theorem, square root of 50 squared plus 20 squared. And so the velocity comes out to 53.85 meters per second. You'll notice that this one is asking for the speed of impact, not the velocity. What is the speed of the impact? And speed is a scalar, which means it does not include direction. So we don't have to find the direction